Okay, welcome to the next video as we're exploring Lagrangian and Eulerian systems and more on fluid particle kinematics. This next video is going to be a lot of stuff. I'm going to try to write it as fast as I can so that it doesn't kill too much bandwidth. So we have fluid particles and their kinematics described as if particles behaving as just some rigid body. So we have the displacement vector, velocity vector, and an acceleration vector. And these all have the usual connotation: x of t at I plus y of t at j plus v of z of t at k. So this is parametric with time. T is the parameter. Velocity is dx dt I plus dy dt j plus dz dt k. Implicit in the velocity is a location. So you can think of each of these being evaluated at x, y, and z. X, y, and z. X, y, and z, or at r if you want to stay in the vector space. And then finally, acceleration is du dt of I plus dv dt of j plus dw dt k, and these are also time varying, and where u of t is equal to dx dt at a location, v of t is equal to dy dt at a location, and w of t is equal to dz dt at a location. The reference of any of these is always the current particle position. So we can even subscript these with a little I to represent the index associated with a particular particle. Now, to try to describe it in a Eulerian point of view, we're looking at positions in space. So the r vector doesn't change appearance month. It's just still x, I, y, j, z, k. So the r vector, just write it here, xi plus yj plus z of k. Notice time seems to be gone. The velocity vector is now x, y, z, and t, and it equals dx dt x, y, z, t, I plus dy dt at x, y, z, t, j plus dz dt at x, y, z, t, k. U, which would be one of these components, x, y, z, t, is equal to dx dt at x, y, z, t. V is that one, W is that one. The acceleration term, x, y, z, t. This is, yeah, I got enough room. I'm going to write this in a special way so I can identify parts. So acceleration is du dt. So it would be partial u with respect to time plus v, u du dx plus v du dy plus w du dz. And that's just taking the vector approach of integrating each component with respect to its particular variable. And that would all be in the I direction. There's also the j direction would be dv dt plus u dv dx plus v dv dy plus w dv dz in the j direction. And there would be dw dt plus u dw dx plus v dw dy plus w dw dz in the k direction. So that's breaking each of these parts and then performing the necessary calculus. And we see something interesting that happens at in this case. There's this du, dv, dw of t. This is called the local acceleration. And there's acceleration that you'll notice has nothing to do with time. This all actually has to do with flow geometry. And this is called the convective acceleration. So, in steady flow, steady means that the time stuff doesn't change. These can all be gone. They're zeroed out. And yet you can still have acceleration. The best example I have of that is you're in a canoe and you're in the Niagara River upstream of the falls, and you are moving downriver nice and leisurely, enjoying your lunch, perhaps a couple beverages. But as you get closer to the falls, the canoe starts to go faster and faster. The acceleration that a person on the side of the stream views is this convective term. It's simply because the flow field is changing as it approaches the waterfall, and the apparent particle velocities speed up by virtue of the water having to accelerate to get over the edge of the cliff. Okay, so just to get a visual idea of these terms, I'm going to try to draw a sketch here. And here we have a coordinate system, x, y, and z. And I want to put a particle in it right here, and we'll call this position 1. And at position 1, this particle has a position, but it also has a a velocity associated, u of x, y, z, in whatever time it is. There's also a v component of velocity and a w component. We're simply going to consider the x component of velocity. And the goal here is to explain the apparent cause of this convective acceleration. Okay, so let's assume that this velocity is such that the particle, let's switch colors, wants to translate upward, delta z units up. It's going to want to translate xward, delta x units that way, and it's going to want to translate y-ward, delta y units that way. So what I'm going to now do is try to draw the box, because I'm going from corner to corner of a rectangular cell. So this translated xward that way, and the color scheme change is important. This light blue is simply to help guide our eyes. Looks like that's about the right y-ness, and that should be about the right z-ness. Interesting word. A little bit of adjustment here. There we go. Okay, so our particle started in this position, and at time 2, we're now in this corner. that point right there in velocity space would have a value of u of x, y, z, and t, where it's this x, y, z, plus whatever the change of u with respect to x, delta x, occurred moving from here to here. Velocity right here would be u of x, y, z, and t, plus the variation of u with respect to z multiplied by how far in the z that it occurred. This point here would be u, x, y, z, t, plus du, dy, delta y. And in fact, these variations correspond to that entire face would have assumed the variation du dx, this entire face up here, the du dz, and then this entire face over here, the du dy. Now we get to position 2, and let's see what velocity the particle has there. Well, it has the particle it used to have, at velocity it used to have, x, y, z, t, plus du, partial u, partial x, delta x, plus partial u, partial y, delta y, plus partial u, partial z, delta z, plus any change in velocity that occurred with time, times delta t. And I can't draw the delta t. So here we have 3 additions to velocity, changes that have the property of an acceleration. That should be a z. And then we have the one that's dealing with time. So for the particle at 1 moving to 2, the particle translates in the x, y, and z directions a distance of delta x, delta y, delta z, and then that translation occurred over a time period, delta t. The velocity at point 2, therefore, is u at x, y, z, t, and we're talking very small changes, plus the change in velocity by moving in the x direction multiplied by how far you moved in the x direction, that's the du dx, delta x, plus the change in velocity in the y direction multiplied by how far you move in the y direction, du dy, delta y, plus the change in velocity in the z direction multiplied by how far you moved in the z direction, delta u, delta, partial u, partial z, delta z, and finally the translation in the time dimension that we can't draw, which would be the partial u, partial t, delta t. The velocity at point 2 also, so we have velocity at point 2 is this term up here, but it's also, velocity at point 2 is u at t plus delta t, and if we subtract off u at t, and then divide by delta t, and we'll take a limit in a second, what we have at u at t plus delta t, because we're at a new time as well as location, minus u of t, all that we have left is going to be this part. Once we make that subtraction, and then I'll divide out the delta t in a second. So you have du dx delta x plus du dy delta y plus du dz delta z plus du dt delta t. Divide that whole thing by delta t, and look what we have here. Delta x over delta t is simply u. Delta y over delta t is simply v, and delta z over delta t is simply w. So we come up with u du dx plus v du dy plus w du dz plus du dt. And so that's all that's happening when the particle goes from point 1 to point 2 in time as well as space. Now this type of description is repeated for the other two spatial dimensions. And the pattern here gives us a way to explain what would otherwise be odd to interpret. Now, the Reynolds transport theorem, coming up a couple of meetings from now, is a way to move between these two systems, where we're looking at a point in space and tuff passes through it, versus we're looking at individual particles. For the time being, I find it useful just to simply accept the calculus. These little plausibility arguments certainly helps my time, because here this was at position t, and this is at position t plus delta t. So that's u at t plus delta t equals that thing. Let's do an example, not merely of this detail, on how to use these ideas. Okay, suppose we have a nozzle. Damn it. That is d units wide at one end and lowercase d units wide at the other end. And it is L units long. And we're told the velocity varies with time throughout the nozzle. The velocity at the base, would be the left edge, is u equals 2 times however much time has elapsed, and the velocity at the tip, it's the small part here, is u equals 6t. So regardless of what time is, the traverse from capital D to little d across L, the velocity changes both spatially and temporally. So the question is, what is local acceleration at the halfway point at time equals 2 seconds? All right, we'll simply just apply direct ideas from kinematics to see what we find. Linear variation means that dv dx is some constant. If it's a constant, that means that v of x equals dv dx, whatever the spatial variation is, multiplied by how far in space we've moved, plus whatever the initial velocity is. So what do we know? We know that v of 0 equals 2t, so that's going to be v naught. Notice v naught's a function. V of L equals 6t. That means that dv dx multiplied by L plus 2t equals 6t. Therefore, dv dx has to equal 4t over L. So now we can substitute this back into our variation equation. So velocity as a function of position equals 4t over L times x plus 2t. The acceleration at x equals L over 2 is d by dt of velocity at L over 2, which equals d by dt of 4t over L times L over 2 plus 2 times time. Those L's cancel. 4 over 2 is 2, so this becomes d by dt of 4 times t, which equals 4. Therefore, the local acceleration is 4 meters per second squared. And that is simply a straightforward application of calculus. The fluid mechanics programs, like that one that drew the pretty lines, is actually working in a Lagrangian field, so it's tracking individual particles. There are computational ways to do that reasonably efficiently, so that's how that's able to work. You eventually, if you read the book and think about this over quite a bit, at some point it's going to start to make sense. I mean, we're delving into vector calculus, which none of us have done recently, and we're trying to work in two worlds, at both the individual particle level as well as the component level, like in a pipe, if you will. All right, that concludes this video, and we will pick up with an example and then finally get into Euler's equation.